Hey, so I'll remind you, the last of the problem sets, problem set 9 is available. It's due Monday, the last day of class. It's just a set of questions about harmonic oscillators. It doesn't have a theme the way that most of them do. It's just a bunch of questions. Second thing, the course evaluation is available now on Colab. Hopefully you've got an email about these things. It expires, I believe, December 6th at just before midnight. So do it before it expires. Once it's gone, it's gone. And the deal is that I drop your lowest problem set score if you complete this. I do automatically get a list of the people who have completed it. So I can tell who's completed, who's not completed it. It's anonymous otherwise. What else? I'll have my Monday office hours in the morning, 9 to 11 in Alderman Cafe if you have questions about the problem set or whatever. Just bring it forward because you're more likely to find it useful. Any other questions, issues, things? All right. So where I left off, or what I was doing last time, is trying to give you an idea of how harmonic oscillators work. What's the point of harmonic oscillators? Well, for timekeeping systems, and we'll see many other contexts, it's nice to have an oscillating system, something that goes through a rhythmic motion over and over again with a special characteristic, that how long it takes to go through that cycle, what's called the period of the cycle, doesn't depend on how big the cycle is. What's known as the amplitude of the cycle, how far the excursion goes away from equilibrium, from center. So harmonic oscillators make excellent timekeepers for clocks. We'll see they're the basis of most musical instruments. They show up all over the place in nature. In reality, most harmonic oscillators aren't quite perfect. They're very close. But if you take them to extremes, things go awry. For example, a pendulum, which is very close to a harmonic oscillator, if you go so far as to have it upside down, it's all crazy. It's not a pendulum anymore at all. It's a ball hanging over a string. It doesn't work. Okay? So harmonic oscillators often are an approximation. It works really well as long as you keep the amplitude modest. So they're used in clocks. Virtually all clocks are based on harmonic oscillators. The most modern of the clocks, I guess, are the atomic clocks. They're not based on harmonic oscillators. But to make one that works, to make an atomic clock that works, you also need harmonic oscillators to help you interact with the atoms and keep track of time and stuff, keep track of the behavior of the atoms. But okay, so the most extreme case clocks are different. But most of the practical everyday clocks really are built on harmonic oscillators. The advantage of that is that they don't have to control the amplitude of the harmonic motion, of the thing that's going through the motion. They still get good timekeeping. All right. The basic conceptual requirements for a harmonic oscillator. First off, it's got to have a stable equilibrium. So it's got a place it wants to go to, and it experiences restoring forces if you take it away, or restoring torques. The second requirement, and this completes the collection, is that the restoring force has to be special. It has to be spring-like. It has to be proportional to how far you take the thing that's doing the oscillation away from equilibrium. As long as you have that behavior, that spring-like behavior, that spring-like restoring force, you get a harmonic oscillator, and the symptom of a harmonic oscillator, the behavior you get along with it, is this amplitude-independent period. Any questions about those ideas? Things? I also talked about frequency being the reciprocal of period. So period is how long it takes to go through a cycle. How many seconds, for example, it takes to go through a cycle. Frequency is how many cycles you go through per second. It's the 1 over period. And we switch from one to the other as we go to higher and higher, faster and faster cycles. It makes better sense often to talk in terms of frequency than to talk in terms of period. All right. I'll also remind you that harmonic oscillators, you can always find an inertial-like aspect and a spring-like restoring force aspect. those are the two pieces you need for the harmonic oscillator. You need something that goes through the motion and has inertia, and you need something that pushes it back towards equilibrium, and that's the spring-like restoring force. And the classic harmonic oscillator, the one that the physicists first think of when they, well, usually, when they think of harmonic oscillators, is literally a mass on a spring. The mass is exactly what you want. It's an inertial thing. The spring is exactly what you want. It's a spring-like restoring force. Bah, you got a harmonic oscillator. This harmonic oscillator, because of the presence of the Earth's gravity, it bounces up and down about a point located here as opposed to a point, if I got rid of gravity, you'd see the motion up here. Because there's gravity, you see the motion down here. But otherwise, nothing interesting changes. So you can basically ignore gravity. Gravity is a nuisance in the for this harmonic oscillator and nothing more. It just, okay. So this thing bounces up and down. The inertial object, which is this brass cylinder, wants to keep going at a constant velocity. That's its favorite thing to do. And the spring wants the cylinder to go back to equilibrium. That's the spring's favorite thing. And so they're fighting with each other. The cylinder tries to keep going down, and the spring says, no, come back. And eventually the cylinder comes on back. And then the cylinder gets used to coming up, and it wants to go to the top, keep going up forever. And the spring says, no, go back to, go back towards equilibrium. So the spring keeps pushing back, and the cylinder keeps trying to keep going straight and steady. And it bounces back and forth about equilibrium, and it keeps bouncing, in this case, until it runs out of extra energy, the energy that's associated with its motion about equilibrium. It's gradually losing it right now to air resistance, for example, and maybe some imperfections in the spring and the support system here. But it'll bounce for quite a while, right? And you can use it to keep track of time. And because it's a harmonic oscillator, having the right restoring force, it bounces. The period for these little bounces is the same as the period for the big bounces. Okay? If I bounce it too much, it will go outside the range in which the harmonic oscillator, basically the brass thingy will go into free fall. It'll go too high. And I probably can do that. Whoa! Right? Disaster. Okay? So as promised, there are sort of limits to practical realizations of harmonic oscillators. Okay. In a harmonic oscillator where you can identify the inertial part and you can identify the restoring force part, if you crank up the inertial part, everything takes longer. The inertial part wants to keep going straight more aggressively, and it takes longer for the spring-like part to pull it back, the restoring force. So if I just do nothing more than crank up the mass, it shifts downward because of that problem I described. Oh my goodness, is it going to? Wow, we're bouncing up and down right near the floor. It's a slower bounce, and I hit the floor, of course. Much slower because the spring is still trying to make it go back towards equilibrium. It's now shifted downward because of gravity. But the cylinder has a much stronger opinion about going straight, so it takes longer. So if you crank up the inertial part of a harmonic oscillator, you get a longer period. Springs have a stiffness, which is how strongly they fight to push back towards equilibrium. This is a very wimpy spring, and therefore it's not very stiff. So if I go to a different spring that's much stiffer, this guy, now if I put the same big mass on it, you can see that the spring is stiffer because it settles with the gravity problem up here rather than on the floor, near the floor. And now, because the spring is stiffer and is more aggressive at driving that mass back towards equilibrium, the period gets shorter. So observations, when you crank up the inertial part, things slow down. The period gets longer. When you crank up the stiffness of the spring, the period gets shorter. Everything goes around the cycle faster. It's okay? And we should be able to find the inertial part in the spring-like restoring force part in any harmonic oscillator. Sometimes they're kind of entwined with each other, and it's a little tricky to find them and get them apart, but they're always there. Do I want to go back to a few tidbits about pendulums? Because I talked about that, and then I don't feel like I did justice to it, to the issues. It is also a harmonic oscillator. It has a mass it has an inertial part that is simply the mass of the pendulum bob, in this case a bowling ball. It wants to keep doing what it was doing, so like everything else. It also has a spring-like restoring force, or very close to a spring-like restoring force. It's not quite proportional to how far you take it away from equilibrium, but it's very close as long as you don't take it like up to the catwalk or the top, the roof of the building, okay? So as long as you work in this range, it's definitely a harmonic oscillator. It has a peculiarity about its restoring force. Its restoring force is gravity-based, meaning that if you turn off gravity, it would have no restoring force. You put the bowling ball up here and it would be happy to sit there all day, right? It's gravity that pulls it back. It's complicated because of angles and geometry and stuff, and it's sort of, I was talking about it riding down a ramp, and it's like this, or rolling back and forth in a bowl. But gravity is responsible for the force pulling it back to center. And that restoring force gets stronger as the weight of the ball gets bigger. For whatever reason, if we put a bigger ball on here and the weight of the ball goes up, the restoring force it's experiencing at this location will be stronger. If we're a little teeny ball, it will be weaker. All right? The other way we can get the weight of this ball to go up is to stick with the same ball, but move to Jupiter or someplace where the gravity is really strong. And in which case, the ball would weigh more and the restoring force would be stronger. So the stiffness of the restoring force on the ball the bob of a pendulum is proportional to the weight of the pendulum bob. So we've got a peculiar situation where changing the mass of the bowling ball, which by itself would slow down the period, accidentally also changes and stiffens the restoring force, which by itself would speed up the motion. And those two effects cancel perfectly. It's the same issue as with all balls fall together. Yeah, you go to the more massive ball, but it also has more weight. So it falls right together with the low mass, low weight ball. So pendulums are a weird case where changing the mass of the pendulum bob doesn't affect the period. That's the bottom line. You've seen this in practice. Have you ever been on a swing set with a whole bunch of kids, all with the same swing? In that case, you're all pendulums. And you're all pendulums that are identical in every important respect except for the mass/weight of the occupant, the pendulum bob. And different kids with different weights and masses will still swing at the same rate. You can all swing as a team going back and forth. You all swing together. Even though you got the little kid, the big kid, doesn't matter. What might matter is if your center of mass is at different heights, different distances from the pivot. That is important. So different kids with different heights may have the effective length of a pendulum. What length is important? Is it the length? Because length matters. And I showed you this last time. I'll come over here and reiterate. As the pendulums get shorter, that's a 4.5 second pendulum. This is about a 2-second pendulum for a full cycle over and back and to come back to where it was. That's about 2 seconds. This guy's like a 1.5 seconds, and this is about a 1 second pendulum. And it all has to do, in this case, with the length of the pendulum. The shorter the pendulum is, the stiffer the restoring force gets, because this pendulum really cares if you take it away from center. It goes up a lot. It pushes back strongly. Whereas this longer pendulum, it's not as stiff a restoring force. You can pull it away from center and not feel it pull back very much. It doesn't care as much. So shortening the length of the pendulum speeds it up. Faster period? Okay with that? What length is the length that matters? The length is it the length between the pivot and the little attachment to the ball, or the tip of the ball? No. It's the center of mass of the pendulum structure. That is, it includes the string, actually, or the rod, and the ball. If you find out the overall center of mass and locate it and measure the distance from there to the pivot point, that's the length. And shortening that speeds things up. Okay, we'll come back to more about pendulums in a second, but I sort of want to start walking through the different types of timekeepers, the different harmonic oscillators finally, for the different clocks. It's kind of a history of clocks to some extent too. Before doing that, a few words about issues of accuracy. So this question here, why are some clocks particularly accurate? And to set the context for that, sort of grandfather clocks and stuff, the really good pendulum clocks can be quite accurate. They require a lot of care and adjustment to get them to be quite accurate. Portable clocks had to give up a lot of accuracy in order to become portable. Pendulum clocks are not portable. They're not portable for at least two reasons, one of which is that the pendulum has an opinion about the point about which it swings back and forth. That point is vertically below the support. So if you have a pendulum clock that's used to doing this motion and you turn it on its side, it's not going to do this motion. It's going to want to do this motion. It's going to be swinging back and forth out the side of the cabinet. So you can't put a grandfather clock, tip it over on its side and expect it to run. It's just not going to do it. And the second, so that in that aspect, it's not portable because you got to keep it exactly vertical. So if you had a portable pendulum clock wristwatch, you'd have to walk around like this all day. Okay? But the other problem is that since gravity is involved in the restoring force, the strength of gravity matters, and the strength of gravity differs at different locations on Earth. I told you way back that if you go from the North Pole to the equator, because of the Earth's spin and its, is it oblate? It's wider at its equator than it is between the poles. Gravity's weaker there. So your clock, which was keeping good time on the North Pole, would be running a certain amount slow on the equator because gravity is weaker and the restoring force consequently gets weaker. Is that okay? So don't try to make portable pendulum clocks. Train of thought, where was I going with this? Okay, so issues with accuracy. People gradually learned how to make reasonably accurate portable clocks, and then better accurate, and then extremely accurate portable clocks. So that's part of the history. That was my train of thought. And so I sort of want to walk you through those things. A few issues about the accuracy. To keep the clock moving, its timekeeper moving, it will not keep going forever without an intervention on somebody's part. This pendulum, which from time to time I get it started, it'll swing the whole class, but it will be swinging like this maybe early on in the class and much smaller later in the class. So where'd the energy go? Because the energy is what's keeping it moving, and its inability to get rid of the energy speedily. It can't do work on the pivot. Really what it has to do is do work on the air. So it's losing energy to the air and maybe to a few frictional effects along the line here. But it will eventually come to a stop, and that's true of all harmonic oscillators in the real world. Or I got to be a little careful with the extreme case, but you're not going to make a clock that keeps its timekeeper going forever. And there are several ways in which the fact that it runs down cause trouble. First off is you have to keep resupplying it with energy to keep it moving, otherwise it's going to stop. And the act of resupplying the energy can influence where it is in its cycle and how long it takes to do the cycle in subtle ways. Let me talk a little about resupplying the energy. A pendulum clock you can get a pendulum swinging in two extreme case ways. One is, I'll do it like this. I can pull it up and let go, or I can simply just give it one big shove, okay? I did work on it during that big shove. I pushed it began to move, and I kept pushing it, and ultimately I did a lot of work on it. It's now packed full of energy, and it will swing all day, having done this. All right, so that's one way, is you just give it a big shove. It will eventually run down, and then you have to give it another big shove. The other way to give it energy is to do it rhythmically. So get started a little bit, and then push it at strategic moments when you can add energy to it. What does it have to do for me to add energy to it? When should I push it to add energy to this swinging pendulum? Should I push it now? Well, I can't do it like that. Now. In order to add energy to it, what physical process do I want to do? Work. To do work, I have to do two things. I have to push it, and what does it have to do? Move a distance in the direction of my push, right? So if I push it now, I didn't put energy into it. What did I just do? I pushed it as it was coming toward me. I did negative work on it. I took energy out of it. This is how you stop somebody on a swing. They're swinging back and forth, and you want to bring them to stop. Do negative work on them. You suck the energy out of them. To add energy, I want to do positive work. I push it as it moves away from me. And if you do that, you can get it swinging harder and faster. Just a little push each time. That's what you do when you're pushing kids on a swing, right? The same thing happens in a pendulum clock. This clock, the system up in there that is propelled by this descending weight gives the pendulum a little push in the direction of its motion every swing. Actually, I think it does it, maybe do it every half swing, every time it reaches an end. And so I have to get it started at the beginning. I have to give it its initial energy to get it moving. But once it's done that, it will swing until this weight hits the floor. Why? Because even though this pendulum is losing energy, it has been aerodynamically redesigned so that it loses less energy to the air than the ball, but it still loses energy. The system here gives it a little nudge with every swing and makes sure that it keeps going. So far, so good? Okay. Back to accuracy issues. The fact that you have to intervene like that you have to give it a little push each time, has a slight influence on its period. Because if you make it swing a little farther than it was before, what do you count as sort of the moment at which it reaches it? What you're counting as the period becomes a little fuzzy because its amplitude is different between one cycle and the next. It's a little tricky to know exactly when to call the beginning and when to call the end. Let me try this with another version of the story, and that is, suppose we don't give it a push. We just let it swing, and it gradually swings less and less and less and less and less and less. Well, if you're trying to count the period, if it swung perfectly, you could sit there with a microscope and watch it come up to the extreme end of its swing and say, now let's start. And then you wait for it to come back to the extreme end of its swing, which is at the exact same location, incidentally, and say, now that's the stop. We know, we've exactly caught the periods. But if it doesn't come back all the way, if it's losing energy and the swing's getting smaller, counting the periods becomes trickier, in part because you have to be at different locations to even find when it hits peak. But the other thing is it loses energy during a single half of a swing, the swing out and the swing back, and they're not symmetric. That means that it had more energy on its way out than it does on its way back of a swing. Its motion isn't a simple wave. It's actually related to the sine wave. It's distorted because it's got less energy later than it does before. That mucks up exactly when to start or when to end the moment you call a period. And it does it in kind of a fundamental way, so that the point of this is the faster a harmonic oscillator loses energy, the harder it is to define, to identify the period, and the worse job it does at keeping time, at ticking off seconds. So the best clocks, and it's not just a matter of you're not good at measuring it, because it's kind of flaky. It's that it's fundamentally not very well the period is fundamentally not very well defined. It's fuzzy as the swing gets smaller. If the swing gets smaller and smaller and smaller over the course of not very many swings. So to get the most accurate timekeepers, apart from being very consistent, is they save energy as efficiently as possible. They go through their motion as many times as possible before they lose enough energy that it's a problem. So you barely have to resupply them. And that means that oscillators that are really good at holding on to energy, like quartz oscillators, are very good at keeping time accurately. Pendulums, not so much. They lose energy faster. You have to really work at them. So that a quartz-based pendulum clock is fundamentally more accurate than a pendulum-based one. It's just, you just can't do super well. All right, that's good enough. Okay, the other thing to point out is that all these clocks have to be, you have to deal with all these external issues. Pendulum clocks, even though it looks like they're pretty good, and they've got, if you get them so they're aerodynamic and they don't waste energy, everything looks great. And now bring along the changes in temperature that come with winter versus summer. Ugh, what do? On a summer day, when it's hotter, everything expands with temperature. I hope this is something that you're familiar with. I didn't really discuss it in the talk about heat and temperature, but it's the case. Stuff gets bigger as you heat it. And the pendulum gets longer when you heat it. And that means it runs slower. So if you make a pendulum clock just without any care, it will run slower in the summer than it will in the winter because of the differences in temperature. You okay with that idea? What do? Well, any decent pendulum clock is compensated for this effect. They use different materials that have different expansions with temperature to make a pendulum. It's a composite assembled pendulum that has different pieces and that manages to keep the distance between its center of mass and the pivot constant even as the temperature goes up and down. And so this is sort of the kind of tricks that inventors come up with, and it all works. So if you looked at the pendulums in fancier clocks, mine's a totally simple pendulum, but in a decent grandfather clock, the support for that pendulum bob is not just a single rod. It's a couple pieces, at least, that are working to compensate for temperature problems. All right? So that's enough about accuracy issues. So how do the classic clocks, the practical ones that show up in the real world, work? Okay, so the first one, of course, is the pendulum clock, and I've talked pretty much about that. It has to stay vertical. You have to put it in place, and in principle, you have to then adjust it in order to deal with the fact that the gravity it's experiencing may well be different from the gravity it experienced back when it was built. So if you happen to have stronger gravity where you live than the company, you need the clock will run fast. If you're not careful, what do? You lengthen the pendulum. How do you lengthen the pendulum? Most pendulum clocks have an adjustment in them. You can actually move a little piece. In my case, there's a little portion of mass, a nut basically on the end of a screw that I can move up and down. And if my clock's running too fast because gravity's too strong, I just move the nut down and lengthen the pendulum, and it slows down. And now it doesn't run fast anymore. So that's the compensation. All right? Once you've got it installed, it's not going to move anywhere, not going to tip anywhere. It should keep good time. Presumably it's compensated against temperature and other issues. You have to keep resupplying it with energy by lifting its weights. This is the story I told you about Jefferson's clock and Monticello, but it'll keep pretty good time, excellent time. All right, but what if you want to move about? So if you want a clock that is portable, it's got to have two features to it that pendulum clocks don't have. First off, it has to not care about orientation. Pendulum clock obviously does. A clock built on this kind of a harmonic oscillator is sensitive to orientation. This one's not sensitive to the strength of gravity, although it'll bounce about a different point if gravity changes. But So gravity doesn't, in principle, change its period, but it mucks up the geometry of the story. So you need a clock that both has no gravitational involvement in the restoring force. Don't have weight part of the restoring force. And it does not care about orientation. And the simplest clock, and one that is sort of the dominant mechanical clock, simple mechanical clock that satisfies these requirements is called the balance ring clock. And I've already talked to death about pendulums. I will talk about balance ring clocks. They use a little wheel, like a little bicycle wheel, that's the drawing here, on an axle. And it has a rotational mass, and the rotational mass is going to be the inertial part of the harmonic oscillator. And it has a little curlicue spiral spring. And that is a torsional spring, meaning that it cares about the orientation of an axle going through it. So the system consists of this wheel that can rotate and has inertia, and the spring that tries to twist that wheel back to a certain orientation. So it's a spring, and it supplies a torque on the wheel that is proportional to how far the wheel is rotated away from its equilibrium. So it satisfies the requirements of a harmonic oscillator. It happens to be a rotational version. There's a restoring torque instead of a restoring force. But it all is otherwise fine. And this disc here on a stiff metal rod is an example of a rotational mass on a torsional spring. The rod wants to be untwisted. It'll fight twisting. And it'll fight twisting the way a spring would, meaning that the restoring force, torque, increases as you twist it more and more and more, and it's proportional how far you twist it. And this guy is a harmonic oscillator, therefore. To get it going, I can give it one big push or a whole series of one big twist, or a whole series of little twists in the direction it's rotating. But I'll just not worry about that. So I'll just pull it out and let go. And you can see it is rotating back and forth about its original equilibrium. And it has a period that's independent of whether I rotate it a little or a lot. It doesn't care. If I rotate it a lot, it's got more, the movement's bigger, and that by itself would take longer, but the torques get stronger, which by themselves would make things happen faster, and they perfectly balance. So it's got a nice rhythm to it. All right? The advantage about a rotational system like this is, leaving this guy alone and going back to that ring, that little wheel. That wheel is designed so that its center of mass and center of gravity are dead smack in the middle of it, right where the axle goes through. So gravity effectively pulls on it. I can't get rid of gravity, but gravity pulls on it right at its center of gravity, which is dead center in the middle of the rotating system, and exerts no torque on it. It's got no lever arm. So gravity pulls right at the center of the wheel, right on its axle, and doesn't twist it. It's like a balanced seesaw. Remember seesaws? Gravity, if you put the center of gravity / mass of the seesaw right there in the pivot, gravity pulls right down at the pivot with no lever arm to twist, and the seesaw experiences no torque. And it turns inertially. And similarly, this wheel, gravity doesn't affect it. It pulls it right dead center at its pivot, exerts no torque on it. Gravity, who cares? So that's the advantage of this wheel, is it's insensitive to gravity. And if you turn the wheel around, it's still insensitive to gravity. So the orientation doesn't matter. It's oblivious, in effect, to gravity. And the restoring force is entirely due to the spring, not to gravity. So we're problem solved. And so this kind of a timekeeper ticks off the portions of time, units of time, very steadily, regardless of orientation. And it's the classic portable clock. And so an example of that is these carriage clocks, which hopefully you've seen these kind of things before. One of the lovely things about eBay is you can find all these kind of clocks. And I want to look down on this clock. Its timekeeper is on top under a piece of glass so you can see it. I used to have wristwatches when I was a kid were all like this. And some of the, well, the ones that nerds like me liked had glass components so you could see the little parts. They're still available, but they're like, well, I should say, if you go looking through the advertising for luxury watches, they're all like this too, or variations on this. And for only $100,000, you can get a watch that's almost as accurate as a $3 watch from Kmart, a quartz watch from Kmart. But anyway, yeah, I love those ads that are trying to imply that when you've got this watch, you are so accurate and precise and chronometer, all that stuff. And it's actually not quite as good as dirt cheap stuff that you get as a premium in a box of cereal or Cracker Jacks. Okay. What I want to do is look down on this. Yes, there it is. Okay. And I can zoom. And I have deliberately not wound the clock. And let's get the light on. Lamp. Ooh, a little bright. So there's the little wheel. And the spring, I hope you can see the spring is a coil of wire around the axis of the wheel. The bearing for the wheel has an axle in it. And the axle is ground to a point at each end and held by a ruby. So that red thing in the center, this guy, that's a little ruby. Historically, they'd be natural rubies. And these movements were described as jeweled movements, and the watches and stuff would say 21 joules or something. The reason they would use this arrangement, a needle sticking into an extremely hard socket. A ruby is aluminum oxide. It's the same, chemically it's identical to sapphire except for the color. It's second only to diamond in hardness, so it's hard as can be. It's got a little socket bored in it, probably with diamonds, and the pin sticks into that socket. Because it's a very tight pin going into a very hard socket, it experiences very little friction for one, and all the friction is very close to the rotational axis, so it exerts almost no torque. The point is, that wheel, if you got it spinning, would spin for a very long time on its sharp point against a hard surface. It's almost a frictionless bearing. All right? So the wheel can turn very freely in that ruby socket. And the spring wants it to go back to this orientation, but if I get it started, if I put energy into it and get it started, it will begin to swing back and forth, and it'll be driven back and forth by some structure that you can see pieces of the structure down below this funny geary thing. Okay, it's a little hard to see the structure working, but let me wind this guy a little bit. So I'll put the energy in. It involves doing work. It's the usual thing. In goes the energy. It's going into a spring, a non-time-keeping spring, an energy storage spring. So I'm putting the energy into the energy storage spring. It's now chock full. And all I need to do is get the wheel started. So how do I get the wheel started? I twist the clock myself. Doop, there we go. So you can see it swing. Well, you're getting sort of stop motion images of it. But it is going back and forth and ticking off time nice and steady. And it will keep going indefinitely because, for one, it's very good at going all by itself. It has almost no energy waste. And for two, it's giving little nudges with every swing, taking energy out of that what's called a mainspring that I wound up, the one that stores energy. And until the energy runs out of that spring, it'll keep going. Okay? And because gravity acts right at its center of mass / gravity, there's no torque on it. Gravity doesn't have any influence. This clock will run fine on its side. All right? Yeah? Once the energy runs out of the mainspring, does it become inaccurate or what happens? It simply stops. it loses energy to the point where finally it can't even trigger the process that releases energy out of the mainspring. And it's a catastrophic change where it suddenly just stops getting the pushes it needs, and then it stops in a few minutes or less. All right. Yeah, we're used to not worrying about winding clocks or stuff. Like this clock, which sits on the wall in my office most of the time, I frequently forget to pull the cord down and I have to start it again. Well, in the good old days, once you got your clock up and adjusted and all that stuff, you surely did not want it to stop because you had no resources for knowing what the time it is to set it to. It's not like you could look at your cell phone. So it was tough. Actually, and then there were eras way back when there were no standard times. So everybody there were lots of local times. Any city or even a household could have their own time. And then there was some great standardization that occurred at some point with the time zones and all that, where there was now an official 12 o'clock. All right. So those are the clocks from, I don't know, 1600 until just before you guys were born, were based on this kind of, this is the technology. I should also say that, boy, I can run out of time fast. One of the most important uses of clocks in the 1600s involved navigation. If you were sailing in a ship and you wanted to know where you were, in part because you wanted to arrive at the right town, and in part because you didn't want to crash on something that everybody knew was there, but you don't know where you are, and so trouble. Well, you can look at the stars and the sun without any trouble and figure out what your latitude is, how far you're north or south of the equator. That's an easily solved problem of astronomy and geometry. But knowing where you are in longitude, which is east and west, is much harder because the Earth turns and the stars overhead look the same to everybody, but at different times of the day. So to figure out your longitude, there are various ways to do it, but one of the approaches required a clock that was very accurate. How accurate? Something in the order of 5 seconds over the course of a month at sea. So you needed really accurate clock, and then you could know it's exactly noon. If we have this star overhead right now, we're at this longitude 73. So it was a terrible problem trying to make really accurate clocks. It was finally solved by a guy named William Harrison. It's a fascinating story. There's a book called Longitude that deals with the evolution of clocks. He finally got a clock this accurate. He started with these big elaborate structures. He finally got a clock. It's little, and it's based on this a ring balance like this, but with tremendous compensations for all the things that can go wrong. The tilting of the wheel, the thermal expansion, contraction, all these problems, the issues of having energy going in and messing up the rhythm, got them all solved, made a clock that was that accurate, and it basically changed navigation. Now you knew that if you go 2 miles east, you're going to be on the shoals of some shore, your ship is going to be destroyed. You can actually aim properly, even though you can't see the shore. All right? So technology of 400 years ago, 350. Okay, so that's balance ring clocks. Can you do better? Well, you can do better with yet another harmonic oscillator. And the harmonic oscillator that's sort of in modern equipment, clocks or otherwise, they're in your cell phones. These things they're quartz crystals. It's actually crystalline quartz. So it's the quartz that you see, sort of the beautiful faceted things. I mean, if you're a New Age enthusiast, you probably have crystals around. So these crystals, quartz crystals, it's very hard. It's not as hard as diamond or sapphire ruby, but it's plenty hard. If you get it vibrating, which it can do, it vibrates for a very long time, like a beautiful bell, before it runs out of energy. So it's able to keep time extremely well. It also does not expand or contract much with temperature. It's very stable in size and shape, and so a good piece of quartz can keep good time. So how do you get it vibrating? Why is it a harmonic oscillator? Well, to sort of start the story, this is just a piece of aluminum, just an aluminum rod, and it is also a harmonic oscillator. A harmonic oscillator, the inertial part of this is going to be sort of the two ends, both of which have inertia, and the spring-like restoring force is just going to be the body of the rod. And what I'm going to try to do, it's not trivial to do this, but is to get the two ends moving very exquisitely small distances, but they're going to both go toward each other and compress the middle, which hates this and pushes out. And they're going to turn around and go out, and they're going to go apart and stretch the middle, which hates it also and pulls back. So the two ends are going to be sort of bouncing in and out rhythmically against the middle. Can you visualize that? To get that going, I could either ping it. You hear that whistle? Ooh, way up there. Or I can give it rhythmic pushes. And the way of doing rhythmic pushes, oddly enough, is like bowing a violin. You hear it? That tone is the two ends coming toward each other, bouncing off, separating, back and forth, back and forth. And it goes forever. Can you still hear it? I can still hear it. So, and that's already hundreds of times per second, and it goes per second. It goes thousands of times before it runs much of its energy down. It's really good at holding on the energy, that motion. And that's an aluminum. You can do better. If I had a crystal rod, a quartz crystal rod, it would be way better. So a quartz crystal rod with this bouncing thing would be a great timekeeper. The problem is, as it gets smaller, I mean, that's a little big for a watch. If you make it smaller, the mass goes down, the stiffness of the effective spring goes up. It goes faster and faster. And so quartz crystals that are little and that are doing this trick vibrate millions of times a second or more. And that's what's going on in some of your watches. In your cell phones and computers and things. But a cell phone doesn't want that super high frequency going on. Why? Because to keep time, it has to count the cycles. 1, 2, 3, 1, 2, 3, 4. Well, if it's going to go millions of times a second, it's got to count to a million every second, or maybe 10 million, or maybe 100 million. That's a lot of counting, which is fine for computers, but every counting process consumes a little bit of battery power. So you don't want to count that fast if you can help it. It consumes the battery power too fast. The switching processes that are involved in counting electronically are energy consuming. So you want to slow it down. But you don't want to slow it down too much. If you slow it down to the point where it ends up in the audio range, people will hear it. It will be annoying. You'll have a watch that will be whistling. And there have been watches over the years that whistled, that had audio frequency timekeepers in them. The famous one was the Accutron watch of about the 60s, mid-60s. So what do? You run one of these quartz oscillators just above the audio frequency range. High enough in pitch that you can't hear it. Maybe a dog can. Maybe they hate quartz watches. I haven't ever tried this. But low enough that it doesn't use a lot of energy to count it. And to get a system that works like that, instead of going with a solid bar going boo, you go to a tuning fork, this is a tuning fork. This is sort of a similar amount of aluminum to that system, but much lower frequency. The two masses that are going toward and away from each other are these two tines sticking up. And the spring is the middle, the U shape. And this guy's got a lower pitch. Right? So, and look how well it keeps the energy. And it's losing energy to sound waves, and it's still able to go for a long time. So quartz watches use a little tuning fork made of quartz, which is even better at keeping energy. That little tuning fork is really little. I got one, so I'll show you one of these. There it is. Oh, focus. Oh, come on. You can do better than that. There it is. That's the tuning fork. Oh, unfocused, dummy. Get the job. Okay, so there, it's a stupid thing. It's a little quartz tuning fork, and they get it moving electrically. Quartz is what's known as a piezoelectric material. It has a relationship between its electrical experience and its mechanical experience. And you can use an electrical effects to make it move mechanically. You've seen that kind of effect with the speakers of your cell phones. They are piezoelectric speakers. They use electrical stuff to shake a crystal and make sound. So this has that. They get it shaking electrically, and then they observe its shake electrically as well. The mechanical motion creates electrical effects. And you've seen this with spark starters. You smack a spark starter and it creates electricity. So this guy is whistling away inside every electronic watch, counting time. All right, on Friday we'll take a good, a running shot at musical instruments.